Hi, my name is Vincenzo Lomonaco, and today I'm going to talk about continual learning, neuroscience, and robotics, and how these three fields can come together to help us design better continual learning algorithms. Before starting, let me just spam a few more words about myself for those who don't know me. I am a continual learning postdoc at the University of Bologna, and I'm also the co-founder, president, and director of research at ContinualAl, a non-profit organization working on continual learning and AI. I'm also involved in some teaching activities in my university for the machine learning and computer architectures courses, and I've been the author and technical reviewer of the online course Deep Learning with R and the book R Deep Learning Essentials, respectively. Finally, I'm also the co-founder and board member of AI for People. Of course, if you want to learn more about myself, you can check out my website, vincenzolomonaco.com. So all the works I'm going to present today are the result of a fruitful collaboration of many people, especially the Continual Learning at Biolab unit at the University of Bologna, coordinated by Professor Davide Maltoni, and with the great effort of two brilliant PhD students, Lorenzo Pellegrini and Gabriele Graffietti. Great, so let's start with a brief introduction to continual learning, especially for those of you that are not really familiar with it, maybe coming from a robotics background. Continual learning is based on the very simple yet powerful idea to never stop learning. So it's the only machine learning paradigm that does deal with an higher and more realistic timescale where data and tasks become available only during time. So we acknowledge the fact that we will never be able to create a perfect model of the world one shot, and that we need to constantly update our biased understanding of the external world over time to face ever-changing environments and novel circumstances. So one key property of every continual learning algorithm is to not have access to previously encountered data. And this in turn let us be constant in terms of computational and memory resources that we deploy to our system, while still being able to incrementally develop even more complex knowledge and skills. However, learning continually is very complex for both artificial learning systems as well as biological learning ones, for what is known as the Stability-Plasticity Dilemma. Essentially, it's very complex to find a trade-off between remembering past concepts as well as learning new concepts and generalize over time, that is getting rid only of the biased information that we have in favor of the more general and robust one. But for deep learning and neural networks in general trained with stochastic gradient descent, one of the first problems that we encounter is catastrophic forgetting. That is, we are too plastic. We learn very quickly from the new data we encounter, and we suddenly erase all the knowledge and skills we learned in the past. So over the last few years, we have witnessed growing interest in continual learning with deep architectures, and a number of continual learning algorithms have been proposed to tame the issue of forgetting. Those algorithms are based on different approaches: the regularization, the rehearsal, the generative replay, and architectural approaches. So I invite you to check out our latest survey on continual learning that you can find at the bottom of this slide. You will find more information about state-of-the-art algorithms and heuristics to tame forgetting and design better continual learning algorithms. All right, so we have made a lot of progress in continual learning over the last few years, but now we can ask ourselves how we can move forward. And what I believe is that we can learn a lot from biological learning algorithms as well as from recent neuroscience discoveries. So let's focus on this slide for a moment, where I try to plot different AI approaches we have been developing over time as the AI community with two different axes: the neuroscience grounding on the x-axis and the practical functionality of these approaches on the y-axis. And even if you focus on just neural networks approaches, the red dots on the slide, you can see that we have made a lot of progress over the last few decades. Just by using neuroscience insights, moving from simple feed-forward neural networks to convolutional neural networks and then deep convolutional neural networks, all based on evidence from the visual cortex, and then being able to integrate into a single representation both time and space with convolutional LSTMs. And we have done the same again with deep reinforcement learning reducing essentially the amount of supervision that we give to our systems. And I think the same can happen with continual learning to move our AI system the next step forward. And we can learn a lot from neuroscience also for continual learning algorithms themselves. For example, we know that the brain employs several mechanisms for learning continually, starting from replaying memory traces to modulating learning through synaptic plasticity, as well as using neurogenesis, that is trying to create new synapses for encoding new information. We also know that it uses highly sparse and distributed representation, and that's of course help taming forgetting and interference of different knowledge. And we also know that it works on high-dimensional and supervised data sequences, so we better make sure to develop our algorithms so they can work in the same regime with these kind of data. But what we don't know is how efficiently implement each of those mechanisms into artificial learning systems, and what is their relative importance and how they interplay among each other. But neuroscience is not the only field that can help us design better continual learning algorithms. And I think that robotic systems also offer a very nice opportunity to work on realistic test beds for efficient and scalable continual learning systems. Robotics, for example, let us design better continual learning algorithms that can work within an embodiment framework, that is, agents that can act on the world and explore its hidden relationships autonomously. Then it helps us work under realistic constraints and limitations of the physical world. For example, designing continual learning algorithms that can learn efficiently and with scalability in mind. They can work under realistic assumption of streaming data collection, and they work in mostly unsupervised settings. Finally, helping us avoiding to focus too much on toy problems. And in the end, robotics is very helpful for the real-world deployment of our AI systems for applications we truly care about. But neuroscience and robotics are not just two fields that can guide us into developing better continual learning algorithms. I believe these three fields are deeply connected, and we're going to see in the near future more and more transfer and cross-pollination among each other. This is because there are mutual benefits for all of these fields, not just for continual learning. For example, continual learning can benefit robotics in developing efficient, active, and adaptive learning algorithms that have been always at the core of many robotics applications. And continual learning can be seen also as the latest machine learning incarnation of developmental robotics. And the same happens in the relationships of continual learning with neuroscience, where continual learning can help neuroscience in providing useful test beds for computational neuroscience theories of learning and memories, of course, and then also better tools, AI tools developed through continual learning can let us better understand neuroscience data. To close the loop, also, neuroscience and robotics share mutual benefits. Robotics for neuroscience can help, for example, in designing realistic test beds for behavioral and embodied neuroscience theories, as well as providing insights from applications into the perception, locomotion, and navigation realm. And conversely, neuroscience can help robotics in designing more efficient and integrated perception and control models, for example. So what I believe is that acknowledging the fact that these three different fields are converging towards a unique goal can help us design better priorities for our current research in continual learning. So, for example, many techniques that have been proposed in the last few years in continual learning deal with the spurious multitask settings in which algorithms are often allowed to have access to additional task-supervised signals, or it involves just a sequence of few and well-isolated big tasks from which to learn from, and the data belonging to each of those tasks is IID. So essentially avoiding the main problem of continual learning, that is trying to learn from a stream of non-ID data over time and in an efficient way. Then most of these algorithms are based on unrealistic and toy datasets that are useful to prototyping new continual learning strategies or understand some basic notions of it. But at the same time, they are unlikely to provide us real insight on how to proceed forward. And then all these algorithms have been mostly tried on mostly supervised settings with an overly focus on the accuracy metric. that is just one of the different axes of evaluation we should consider developing, truly continual learning agents. What I believe to be a better focus for continual learning research today is working under single incremental task scenarios. That is not involving necessarily multiple tasks, but learning from high-dimensional data streams, highly non-AD data, for example, natural videos from realistic data sets, and possibly moving towards mostly unsupervised settings, exploiting, for example, time as a surrogate supervised signal. Then another important shift of our priorities will be focusing on scalability and efficiency rather than just accuracy. So having redefined our priorities, we can now design benchmarks and metrics that can help us move towards that direction. So we can now think at our continual learning setting as just a stream of perceptual data that we are allowed to process in small incremental batches. And based on the content of those batches, we can define three different scenarios. The new instances scenarios is based on examples that we encounter in these incremental batches that are belonging to classes we have already seen in the initial batch. For the new classes instead, what we encounter are new examples of classes we have never seen before. For the new instances and classes scenario, the most realistic one. What we encounter in each incremental batch are examples of classes we have already seen before, but also examples of new classes we have never seen before. Core 50 has been one of the first video benchmarks that we proposed back in 2017 and has been specifically designed for continual learning and to work under these scenarios. So providing different benchmarks for rapidly prototyping continual learning algorithms. And here you can see the 11 different sessions that we collected for 50 different domestic objects in very different environmental conditions, varying background, illumination, rotation, and occlusions, so that we could really assess the capability of a continual learning agent that can somehow learn over time invariances for those objects. But Core 50 is not the only dataset and benchmark you can use for continual learning, respecting the principles and the priorities we have defined before. For example, you can use Stream 51, which is a very interesting continual learning benchmark, using different videos recorded in very unconstrained environments. Then you can use the Open dataset, for example, in which you can assess your continual learning algorithms on a robotic environment instead. In fact, all the different video sessions of domestic objects, in this case, have been collected directly on a robotic platform. And then last but not least, the ICAP transformation dataset, which is a very large collection of video sequences of objects, also in this case collected to the from the ICAP robot, and containing different variations that can be very useful to assess the ability of a continual learning algorithm to generalize over time and create robust representations of those objects. But working natural video sequences is not enough, as we were saying before, for designing better continual learning algorithms. We also need to define and share among the community better metrics for assessing and comparing our continual learning algorithms. So in this paper, don't forget, there is more than forgetting. What we try to convey is the need for new metrics that are accounting especially for efficiency and scalability. For example, we should start trying to take into account the amount of memory we consume, and also if this consumption of resources is growing over time. And the same goes for the computational efficiency. So we would like to end up with a kind of a spider plot that you can see on the right, where we assess a continual learning algorithm not only for accuracy, forward transfer, backward transfer, positive or negative, but also for computational efficiency and memory usage. So let's see now some results and algorithms we have proposed over the last few years for addressing these kind of scenarios with these priorities in mind. and moving towards real-time continual learning over natural video streams. In our latest work, Latent Replay for Real-Time Continual Learning that we submitted to IRIS this year, we tried to focus on continual learning algorithms that could work on the edge. That is, learning with very tight computational and memory budgets. So we ended up with an application for Android devices, smartphone devices, that could work with no hardware acceleration and in real time could update state-of-the-art mobile net after we expose it to 20 seconds of videos. And here you can see our algorithm in action. We're not going to see the whole video here, but you can watch it directly on YouTube at the link that you can find at the bottom of this slide. So what I wanted to show here is the application very quickly that the operator is using here. So essentially, we have a bunch of classes that have been pre-trained into our model. Then the operator shows the object it wants to recognize inside this little square, and the network can guess among the classes that it has already encountered. But what's interesting is when we learn about new classes that we've never seen before, or we update the knowledge on existing classes as well. So in this case, the operator is showing an adapter that the network is not able to recognize somehow. So you can see that is exchanging it for a smartphone. But then we can improve, in this case, the ability to recognize the adapter class by showing 20 seconds of video of this new adapter just by rotating it and changing the different perspectives so that the network can build continually invariances and robust representations for the adapters. And here the gathering process finishes, as well as the training after 1 second. And now we're able to recognize the adapter as well as recognizing previously learned adapters, so we don't have forgetting. So the app comes with a custom version of the Café framework in which we allow training on the Android device with a C++ implementation of the AR1 algorithm we are going to discuss in a moment. And then it uses a mobile net version 1 net, pre-trained on image net, and then later tuned on 10 different categories of the Core 50 dataset. Then during training and updating our model with the new video sequences, what we do is to, from the 20 second, just take 100 frames, so 5 FPS, and we use latent replay, in this case combined with other techniques, using 500 activation volumes that are kept and occupies around 2 megabytes, so very reasonable assumption for an embedded system. So the AR1 algorithm and the latent replay mechanism that we deployed for this application have been designed to be extremely light on resources, with a reduced memory footprint, minimal latency, that is training time, and a very low energy consumption. And the accuracy performance trade-off for our continual learning algorithm can be chosen based on the target platform and the problem at hand. So this is very suitable for any robotic application and embedded application, as well as for ultra-low power devices. So what about the AR1 strategy? We started to develop this strategy back in 2016, trying to mix an architectural and regularization approach, and we continued developing advances for these algorithms and better implementations. You can find more information about this strategy in our paper, Continuous Learning in Synchronous Incremental Task Scenarios. But let me spend a few more words on the advancements that we made with AR1 from 2016 to today. So we started back in 2016 with copy weights with RAINY, CWR, a simple but effective weights normalization algorithm that could work on new classes and new incremental, new instances and classes scenarios. Then the next year, in 2017, we proposed an extension on CWR called CWR Plus and AR1. AR1 was proposed to combine an architectural and regularization approach to address continual learning scenarios. And essentially, was based on CWR+, but also combining a regularization approach for the representation layers of the network. Then in 2018, AR1 star was proposed as an extension of AR1, essentially making AR1 working agnostically in all the three different scenarios: new instances, new classes, and new instances and classes. Then in 2019, AR1 was somehow expanded to also comprehend a replay mechanism in it. But while we consider replay from the input space to be somehow nor efficient nor biologically possible, what we tried to design was a latent replay mechanism. And so we have been able with this mechanism to work on very challenging settings involving, for example, more than 391 batches of 300 images each. But let's now focus only on the latest advancement of AR1 with latent replay, explaining it in better details. So we know that rehearsal or replay requires to store some representative examples from the past. And this works quite well for taming forgetting. ICAR, for example, is one of the best known strategy employing this technique. However, despite being, as we hinted before, already not really plausible from a biological perspective, it requires extra storage. For example, for ImageNet, if we store 20 patterns per class, the total storage is already 3.8 gigabytes, which is not ideal for robotics and embedded applications. And something that is not often considered, it also requires some extra forward and backward steps. So essentially, we're increasing the amount of computation that we need, relearning things we have already learned from. So this is because we need to mix new and old patterns, increasing the total number of epochs when we learn. So the main idea of AR1 with latent replay is to store activations volumes at some intermediate level and not raw images. And this is the functional diagram of AR1 working with latent replay. So here on the left, you can see our pre-trained neural network on ImageNet, and we can conveniently divide it into different parts: the low-level generative features as well as the class-specific discriminative features. Oh, actually, we have also the output layer here, which is a third component of this network. And then we approach these different blocks in different ways. So for the low-level generative features, which are already robust enough, we are just going to fine-tune them slowly. And then for the class-specific discriminative features, we can regularize them over time with a regularization additional loss term. And for the final up-to layer, we're going to use the standard CWR star algorithm. And you can read more details about this subcomponent of our AR1 algorithm directly in the paper. Then what we do is to extract some activation volumes at this layer in the network and randomly from the images that we encounter over time. And then we use all these examples extracted at this level when we encounter new images. We have a new batch of data we want to process, concatenating them directly on the fly during the forward pass. Latent replay has several advantages with respect to native replay from the input space. First of all, it's very efficient. Extra forward and backward steps take place only in the upper layers in the network. It requires also less storage, and activations can be quantized, compressed with negligible accuracy losses. A nice property of latent replay is that we can decide from which level to replay our activation volumes. And this, of course, impacts on the performance and on the trade-off between the resources consumption and the accuracy. Here on the left, you can see a plot in which we show the total accuracy on the Core 50 dataset over time, encountering 391 batches of 300 images each. And we show the accuracy performances of AR1 star, CWR star, we discussed before, and the cumulative approach of just retraining our entire model from scratch with the accumulated data. And we show that with just plain replay from the native input space with just 1,500 images, around 1.2% of the training set from Core 50, we can substantially improve the accuracy performance at the end of the training procedure. And we're just 10 points away from the cumulative approach, which can be thought as to be our upper bound. Here on the right, instead, you can see a plot in which we show the accuracy performance of the same AR1 with the replay strategy, but where we change the level from which we replay our activation volumes. So the AR1 star-free images is essentially the strategy in which we replay the raw images, so the same that you can see here on the left. And what we try to do here is to move the replay layer across the network from the input space towards the output layer. And you can see that the performance are degrading somehow proportionally. And so the nice thing is that we can find a nice trade-off in which we lose just a bit of accuracy with respect to the raw input images, what we spare a lot of computation and memory resources. We're now working to even improve AR1 with latent replay, moving towards generative replay. So the idea is to substitute this external memory in which we store the activation volumes with an additional generative model that maybe can be just a branch of our neural network that is in charge of regenerating back activation volumes at that particular layer that can be used for rehearsal purposes. This idea is very interesting for continual learning because it allows us theoretically to imagine patterns that have never existed before, even exceeding possibly using an external memory for replay. But before making this idea possible, a number of practical issues have to be solved. First of all, training a model, a generative model to produce useful images or high-dimensional patterns is not that easy to scale to complex data sets. It is okay for a MNIST of Cypher 10, but not so much for Cypher 100, ImageNet, or Core 50. Then generating features instead of raw data has been proved to be useful for continual learning. However, most of the algorithms that we propose in this area are generating patterns at the semi-last level, which are very simple to reproduce and are very low dimensional. So what we would like to do is to train the generator online and GAN approaches may be too slow to do that, especially considering a long sequence of very small batches. So the challenge is to generate complex activation volumes in near real time. And this is very challenging and something we are working on at the moment. Quickly moving towards the end of my talk, let's consider a few more research directions that can be very interesting to pursue in the near future. First of all, moving towards unsupervised training using self-supervised learning or sequence learning techniques exploiting temporal coherence, or moving towards open set classification and sparse human supervision with active learning. Another interesting line of research would be to better find hybrid continual learning strategies, mixing several mechanics for addressing forgetting and build robust representations from non-ID data. So I hope you enjoyed my talk trying to define better priorities for current continual learning research and showing some examples of continual learning algorithms that can work within these principles and towards these goals. So if you're interested in these topics, don't hesitate to join ContinualAI, a non-profit research organization and open community on continual learning for AI, counting more than 1,000 members across the globe in 17 different time zones. And of course, if you have any question about this talk, join the next live Q&A session as soon as this video ends, or send me directly an email at vincenzo.lomonaco@unibo.it. Bye.